Abdul Shafiq under ICOSA Shenzhen Conversion and Separation Technology, supervised by Dr. Nabila binti Zaini, will be presenting a review on challenges of syngas production derived from commercial plastic waste, in specific to the development of kinetic modeling. This study is conducted between me, UTM, and Petronas Research Sdn Bhd. Adapted from the Journal of Sustainable Resource Recovery and Zero Waste Approach, syngas is also known as synthesis gas, which is mainly composed of carbon monoxide, hydrogen, and carbon dioxide. Sometimes it may also contain nitrogen and methane. It is one of the most cleanest energies as it emits low sulfur and carbon dioxide content as a byproduct. Generally, syngas is produced through a thermochemical process known as gasification. Throughout this process, syngas converts any carbonaceous substances contained in either solid waste or petroleum product in a controlled condition. In 2019, Ericsson stated a figure of 300 million tons of global production of plastic per year. In addition to that, the Central Pollution Control Board documented around 25,940 tons of plastic waste was generated per day globally. As shown in the diagram on the right, at the end of 2016, polyethylene holds the highest percentage of plastic waste accumulated globally, followed by polypropylene. Do you know what materials in our daily life consist of polyethylene and polypropylene? Polyethylene is diversely used in the production of materials such as trash bags, plastic bags, water bottles, and even insulators for electrical cables, whereas polypropylene is usually used in the food containers that we use when we bring takeaway food home to enjoy with our families. To take benefit from this abundant waste, characteristic of these plastics hindered by the van der Waals force makes the carbon chain easy to break, thus can be used to generate energy from waste. Malaysia has been placed at 8th among 10 countries that mismanage plastic waste, whereas global is facing a very low recycling rate, which falls at 9% out of 9 billion tons of plastic waste generated, thus making this research beneficial in reducing the amount of plastic waste in Malaysia as well as globally. Besides, insufficient current energy dealt by Petronas due to its financial crisis in processing crude oil due to the low demand and supply affected by the pandemic COVID-19 has shown a decline of 3% for gas market compared to the 2018, as said by Zaharia Liza, one of the Petronas board of directors. On top of that, this research is conducted as to fulfill the lack of research and expertise in syngas production, especially for mixed plastic waste, as most syngas which are readily available are derived from the biomass. Recently, members of Campus Sustainability from UTM has posted a memorandum during the last Ramadan in avoiding of any usage of single-use plastic bags. In June 2021, Petronas has launched a new campaign called Net Zero 2050, which aims to safeguard the environment with a green energy as well as creating continued value to the energy produced in sustaining our way of life, which is coherent to the research conducted. Syngas, a gas with a low sulfur and carbon dioxide emission. Move on to the first objective, which is to determine the weight degradation of commercial mixed plastic waste to the increasing of the temperature via thermogravimetric analysis TGA. There are 4 plastic samples tested, which is a pure PE, pure PP, 75% PE and 25% PP, and 50% PE and 50% PP. All of these samples will be treated under conditions of 30 degrees Celsius up to 1000 degrees Celsius at 1 atm with a nitrogen, which acts as a pyrolysis agent, is supplied at the rate of 60 ml per minute. Then the next objective is to evaluate the challenges in syngas production based on development of kinetic model by critical review method. At this section, syngas production, effect of the blended ratio among PE and PP, as well as the kinetic model development will be evaluated via the critical review method. Last but not least is to suggest on the syngas production optimization in lab scale and industrial scale. This is the research flowchart whereby the sample is prepared by grinding and sieving at a size of 1 to 2 mm. Then all samples will be average of 8 mg per samples will be pyrolyzed inside the TGA at pyrolysis temperature ranging from 30 degrees Celsius up to the 1000 degrees Celsius with a heating rate of 20 degrees Celsius per minute and the input of 60 ml per minute of nitrogen in a platinum pan. The rate of carbon conversion among samples will be determined based on the data obtained from the TGA. Lastly, is the process of critical review whereby the evaluation of the effect blended ratio, kinetic model development and suggestion on syngas production optimization. In this slide, it is proven that 100% PE by composition shows a weight degradation of 92.48% with an initial mass of 8.711 mg and ended at 0.5915 mg. Whereas for 100% PP showed a lower weight degradation compared to the PE, which falls at 83.39 percent with an initial mass of 5.6170 mg and ended at 0.09601 mg. For 75% and 25% PP by composition, which also showed much lower degradation compared to pure PE, which is at 89.94%. However, for 50% PE and 50% PP shows an increasing trend from the previous composition, which falls at 94.05% due to the decrease in the energy needed to break bond compared to the previous sample. Summarize, the graph on the right shows a compilation of TGA results for mixed plastic waste, which shows that all samples are fully decomposed around 500 degrees Celsius and fully degraded roughly at about 650 degrees Celsius, whereby the 50-50 ratio shows the highest thermal degradation, followed by the pure PE, then 75% PE and 25% PP, and the least is the pure PP. After further analysis, the data has concluded that pure PE has the highest rate of material weight changes upon heating, with a 57.64 weight per minute at 428.44 degrees Celsius. By averaging all samples, the optimum temperature for syngas production derived from PE and PP lies in between temperature of 420 degrees Celsius to 430 degrees Celsius, with any composition that favors to PE. Let's move on to the next objective, whereby to evaluate the challenges in syngas production from mixed plastic waste. All organic waste are suitable feedstock in syngas production due to its highest purity of carbon C1 and hydrogen component, which is the main component of syngas. The flexibility of syngas in producing other value-added product has been insufficiently exploited due to its complexity, creates challenges in transforming the feedstock into syngas by conventional procedure. Therefore, I personally suggest to remodel the kinetics and optimizing the reactor operational conditions, such as the involvement of biological fermentation or chemical catalyst or gasification temperature in boosting syngas production that are applicable for natural gas product, biomass, or even municipal solid waste. In reviewing this research, catalyst preparation method will also influence the properties of catalyst, which will give an impact to the activity of catalyst. As a suggestion, impregnation method treated towards the catalyst using the rising pH will also improve the syngas yield. Besides, this section evaluates on the objective 2, which is the effect of a blended ratio among PE and PP. The diagram on the right is a base reference for gasification, where the data obtained from the TGA conducted experimentally during pyrolysis is coherent to the data analyzed. The reason behind this story is that PE has a longer hydrocarbon chain compared to the PP, thus higher carbon will be available to convert during gasification when treated with the carbon dioxide to form carbon monoxide, which is a component of syngas. Addition of any other products such as wood pellet and pet coke may also increase syngas yield due to its heavier and simplicity in its elemental composition, and compared to any other available products which may have contaminants that may impact the efficiency of syngas production. Addition of these two products resulting to the higher rate of reaction, as well as increasing the optimum temperature required during gasification as compared to the mixed plastic waste, in return higher cost of operation in producing syngas. For the kinetics of PE and PP, the data from the TGA showed that the PP start to melt and decompose faster, which roughly at 200 degrees Celsius, whereas PE at 350 degrees Celsius. And most samples are fully decomposed at the same temperature, which lies around 500 to 500 degrees Celsius, and the carbon black is formed above 600 degrees Celsius. This proves that the gasification of raw sample of mixed plastic waste is best conducted at gasification temperature ranging from 420 degrees Celsius to 430 degrees Celsius in maximizing syngas production from mixed plastic waste, specifically for PE and PP. Lastly, the conversion rate of samples to carbon can be evaluated based on the data obtained in TGA by plotting the graph of carbon conversion rate against exponential temperature. It is believed that addition of carbon dioxide instead of just the sprinkle of water or steam during gasification may improve syngas yield. By referring to the Bourdon reaction, the carbon dioxide will react with carbon, with the sample itself in producing the carbon monoxide. Lastly, is the process on syngas production optimization during the kinetic model development. The coefficient of determination, which is the activation of energy, can be used in determines the correlation of data model from the kinetic model to the experimental model. Plotting an Arrhenius plot, which is a graph of ln K against exponential temperature, is useful in determining the best kinetic model developed by fitting the activation energy based on the results obtained in TGA. From the results, it is useful that samples with the lowest activation energy will reflect to the highest conversion of carbon to carbon monoxide and can be used as a syngas best model. This research has concluded that the addition of nickel and cobalt in a bimetallic catalyst supported over alumina shows an improved properties for the carbon monoxide hydrogenation, which resulting to the increase of the syngas yield. That's all from me. Thank you.